Dr. Stevens.
It's still after. Wait, did you still after all?
Okay, guys, we need to get started. Was there a question?
It's about the test class.
I'd probably prefer you stop by. If you have questions about the test, please stop by. Key is posted. Okay, please learn from your mistakes. We need to get started. Stop by. I sent an email out just now. Test 3, we will not have comprehensive spec problem. We'll have IR only. Acid derivatives, IR only. There's problems in the workbook. Test 4, we'll go back to the comprehensive spec problem. Okay? I sent 2 handouts for you to print on your own. Let's see where we're at. Acid conversion, carboxylic acid derivatives. Interconversion table there. Preparation of carboxylic acids, mainly review. Chemistry of acid derivatives. I think we're pretty much through with the other white sheet for now. We'll be getting into the green as needed. Chemistry of acid derivatives. We have another NAS reaction, but it's not called NAS. NAS refers to the other one. Nucleophilic acyl substitution. We're going to have a carbonyl with some type of group that we're going to substitute. Okay? By nucleophile. The nucleophile is going to substitute it. Carbonyl is often called an acyl group. So that's your mechanism. How can we substitute this for the nucleophile? It's a substitution reaction, yeah? But it ain't SN1 or SN2 because you don't do those mechanisms on a sp2 carbon, right? Okay. It's an addition elimination. We saw this very early on when we were doing like methynyl chloride, tosyl chloride, those type of things. The NAS aromatic mechanism is also an addition elimination. And importantly, we had to have a ortho or para electron withdrawing group so that we can put the negative charge on a heteroatom. That's the only time you're going to be able to do a nucleophilic addition to a double bond. Okay, mechanism. The nucleophile is going to attack the carbonyl. Now the carbonyl is polarized. You have partial positive on the carbon, partial negative here. Nucleophile is going to have high electron density. It may be neutral or it may be an anion. It'll be attracted to the carbonyl. We can add to carbonyl, and then the electrons are going to move up onto oxygen. We're going to push them up onto oxygen. Because if you add to this carbon, which bond we're going to break? Pi bond or single bond? Pi bond. The weaker bond is broken. So we do that first. We do not immediately kick off that. If we did, we'd be doing what would look like an SN2. We don't. We do an addition. You get this structure. This is typically your rate determining step. This is called a tetrahedral intermediate because the carbonyl carbon is now tetrahedral in this structure. Addition. Now we come back down and reform the pi bond and kick off the better leaving group. Now it could be that the nucleophile is a better leaving group. If we kick it off, we just become backwards. That's possible, but if we want a new product, we'd have to kick that off. Typically R is just carbon. This is going to be something like a halogen or an oxygen, a heteroatom, something that's going to be more prone to leaving. Overall, we get an acyl substitution by an addition elimination reaction. The elimination is typically fast because anytime you can make a pi bond with a lone pair, kick off a leaving group, that's typically fast. We'll say that many times. Which step does a leaving group leave in?
Second step.
The fast step. Just like the NAS mechanism. Which is different from SN1, SN2 because in SN1, SN2 the leaving group leaves in the rate determining step. Those mechanisms have very strict leaving group requirements. NAS does not, neither does this. We'll see lots of things leave here. If you've ever seen it be a minus, it can probably leave here. We'll even see carbons leave here. They will be stabilized somehow. It won't be just a plain carbon. Okay? Leaving group leaves in the fast step, so you don't have restrictive requirements. Okay, we can plot this, 2 steps. Should be pretty straightforward. Looking like the first step is your rate determining step, higher activation energy. Give the tetrahedral intermediate, which is charged, so it's higher energy. And then when we fall downhill, it doesn't take much energy, so it's a low transition state energy. To fall downhill, to reform the carbonyl, and to get ultimately a new group on your carbonyl. All right. I just said this stuff here about rate determining step. Actually, your best leaving group for this type of reaction, which halogen is your best leaving group actually? Actually, fluorine is the best leaving group. Not so much because it's leaving. This doesn't influence anything. It's a fast step. With the fluorine here, why is that the best leaving group, or group you're going to ultimately replace? Least stereochemics is a possible argument because it's a huge iodine, yeah, but we know in SN2 iodine's better. And you can make the same argument, well, it's bigger, shouldn't it be slower? Well, no, it's actually better there. Why is that better here? Because it pools and it creates more partial positive there. Its ability to leave is really not important. It will leave, and that's fast. Okay. We may even see carbon leave. For example, if you look, we'll eventually see the haloform reaction, and that's where actually a carbon is going to leave. But it won't be a plain carbon. It'll be stabilized somehow. And you typically don't see an H leave, at least not in this class. Hydrogen's not going to leave in this class. Okay. Reactivity of acid derivatives. Your acid chlorides are more reactive than your, this is an anhydride. Anhydride, we'll cover these in detail. This has an oxygen bonded to 2 carbonyls. Again, we'll see that a little bit later. It's more reactive than an ester, and an ester is more reactive than an amide. Of course, in that very front page, they were listed according to reactivity index block, right? And this was the highest up. There you go. Note that the carboxylic acid is not listed here because it's carboxylic acids. It's actually difficult to do the mechanism we showed because of a particular reason. Because it has the acidic proton. We'll talk about that. Basically, why is this more reactive than, say, the amide on the other end? Okay? Well, I've got it showed here. Okay, if you talk about the acid chloride, well, first off, they all have the carbonyl. So there's no use talking about it. The difference is the chlorine. Well, the chlorine pools. We know it can also donate, but it withdraws. That's its main effect when you can do both. So it withdrawing is going to make more partial plus here. Let's skip the anhydride. Let's look at here. What's the net effect of an oxygen when it can both withdraw and donate by resonance?
Donate.
Just like with aromatics, the net effect is donating. So if you got any partial plus here, and this is donating, that's the net effect donating, it's going to sort of quench the partial positive. So there's not as much partial positive here. Now this is a resonance structure showing the donation. Now every carbonyl has this. We can just move these out. here's a resonance structure where we polarize the carbonyl. But every carbonyl has that. Okay? Now, look at this plus here. Is it really a lot of plus? Or is this guy donating to quench it? And if it donates, then you get that resonance structure. The donation of this quenches some of this partial plus. It's not as much, so the nucleophile is not as attracted to it. Now, let's go back to the anhydride, which is between the two. Anhydrides are more reactive than esters. First off, even though it has two carbonyls, you only consider one of them. We'll talk about it. Okay? We can envision some partial plus here. We know that oxygen can donate. But which oxygen is going to donate more? That one or the ester? Keep in mind that this oxygen is also donating this way. Since this oxygen is donating this way, it doesn't donate that way as much. This oxygen donates more because it's not donating that way in conjugation. So the anhydride carbonyl tends to be more reactive than the ester. But it's not as reactive as this guy. Then the least reactive is the amide. Because if we can envision this being like an NH2 or some substituted amide, which one's going to donate more towards the positive? Now in aromatic, we consider both of these as group 1. But if you look at them in closer detail, which one donates more? Which one is willing to donate more?
No, it's amine, obviously.
Who's more willing to lend you money? A very greedy person or someone who, here, I don't care, take my money. The greedy person ain't going to want to lend you much money. The greedy oxygen, which is more electronegative, doesn't want to donate as much. The nitrogen, any partial plus here, that nitrogen just here, take my electrons compared to the oxygen. There's least partial positive here in the amide because the nitrogen is quenching it. It's giving it the electrons. Now, hopefully, you're getting to the point where when you look at this, that's not all just fixed in stone. These electrons are like perturbed, right? Electronegativity, resonance. That's a snapshot, really fake view, right? Okay. Well, most all of our discussion is really talking about the sort of the nuances of the structure, the electrons. So, amide is your least reactive of these we're looking at. Down here I'm just showing, this is where I bypass the positive, the resonance structure with plus here, and go ahead and bring them in. It gets to this resonance structure here. With amides, this is a major resonance structure. Now, I've got to be careful. It's not D major. This is D major because there's no charges. But this is a pretty predominant resonance structure because the nitrogen loves to donate. The greedy oxygen actually gets a negative. So these electrons are being pulled this way. And so this is a very important resonance structure. We'll refer back to this. Now, I actually have proof. Have we ever showed proof of a resonance structure before? Some. I mean, we talk about the effect on acidity. I actually have NMR proof of this resonance structure. Okay, before we go on, let me ask you this. If we did proton NMR of this, how many signals would you expect? Proton NMR. One for that guy? Yeah. How many for these methyls? One? They look equivalent? Okay. The NMR is on the next page. By the way, this molecule is, what's the name of this molecule? Abbreviation. DMF? Yeah, here's an NMR DMF. Here's the H. Kind of looks like an aldehyde. It's not really an aldehyde, but it's way downfield, not quite aldehyde region. And then here's water. You're always going to have water in an NMR. Okay? Because here's your sample, here's your light. Guess what's between the light and the sample? Air. What's in air? Water. Okay? Get a little water. There's also water in the solvent. So we just ignore that typically, yeah. And then here are two methyls. They're not equivalent. Why are they not equivalent?
Because they're not an equivalent.
Because this resonance structure contributes a lot. What if this was the 100% structure? Would the methyls be the same? No, double bond, can't rotate. One methyl is cis to the oxygen, the other one's trans to the oxygen. Okay? Well, it's only one structure. But what we're getting at is the structure has enough double bond character between here that the rotation is restricted. And we see that in NMR, making the methyls non-equivalent. That's pretty good evidence of what's going on here. Resonance. Okay? Everybody agree? Good evidence? Okay. Okay, we'll be converting from one acid derivative to another. We may go back to the carboxylic acid. What's not included here yet is the chemistry of nitriles. That is an acid derivative, but we're only considering those with carbonyls right now. Okay, one thing, one rule. You only convert to a less reactive derivative. This meaning in one step. Now you can convert the amide to this. You can go backwards, but not in one step. You're going to have to go back to the carboxylic acid and then to the acid chloride. But in terms of one step, you only convert to a less reactive derivative. The acid chloride can be converted to all three, because they're all less reactive. We'll explain why. An ester can only be converted to an amide. You cannot convert an amide to the acid chloride. You might say, well, let's react it with this. Boom, kick off the nitrogen. Not going to work. Not going to work. Why will it not work? Well, right here. That sort of explains it. Let's illustrate it. Even if you could get this. First off, the amide is not that electrophilic. Now that doesn't mean, because it's relative. We know it's less reactive than those, but who knows? It may still be pretty darn reactive. Well, actually, it's not. It's not that electrophilic. As you want to get a chlorine on here, you're dealing with a not so good nucleophile. Even though it's an anion, it's the conjugate base of HCl. It's not a strong nucleophile. So you got a pretty weak substrate, pretty weak nucleophile. Things aren't looking good. But even if we could get it to add, get the tetrahedral intermediate, when this comes down, which one's it going to kick off? The chlorine's a better leaving group. Even though this is a fast step, it's still going to kick off the better leaving group. The better leaving group is the one that's going to be more stable as the anion. Then Cl- is more stable than N-.
Could you use HCl with a protonate? Oh, the pi bond conjugate.
We'll talk about that, but this is why you don't do it. On the other hand, let's look at a good reaction. Reacting an acid chloride with ammonia. This is going to be good and easy and very typical. First off, very electrophilic carbonyl. Ammonia is a pretty darn good nucleophile. Even though it's neutral, it's still, that's a better nucleophile than Cl-. So you've got some good reactivity here. I sort of take a shortcut. Let's draw two arrows here because I've lost the H. All right? This is not good. I'm taking a shortcut here. We're going to have to talk about the proton. Okay? And I kind of glossed over it here, and I wish I hadn't. But at this point, when this comes back down, which is a better leaving group? Cl or nitrogen? Yeah. Cl is your best leaver because it's going to be most stable, so it's going to kick that off, and there you go. You accomplished the reaction. Everything is set up for that reaction to take place. And you're going from a more reactive acid derivative to a less reactive acid derivative. Okay, you mentioned protonation. Let's look at this general idea. Protonation may be an activation step in many of these reactions. If you're under acidic conditions, for example, an ester will not react with pure water. You may say they're going to replace the NEO with the OH. Here's a proton here. And maybe produce the acid plus methanol. That's an acyl substitution reaction. But it's not going to react. Esters typically don't react. One of the main reasons or arguments is, well, the ester is just not that reactive. And what we're going to learn is acid chlorides and anhydrides will react with pure water, but esters and amides, being less reactive, will not. On the other hand here, if you include an acid catalyst, so now this is H3O+, right? You can get the reaction. What does the acid catalyst do? You protonate the carbonyl. And if we protonate the carbonyl to get to this structure, what have we done to this oxygen? We've made it mad. We've made this electronegative oxygen mad. It's like, hey, I need some electrons. So it's going to pull more on this pi bond, which is polarizable. Okay? We made the oxygen more electron demanding. It pulls more and it generates more partial positive. And these are actually resonance structures. More positive on the carbon. Now the water will attack it. Where here, yes, it's partial positive, but it's not as much as here. There's more partial positive here. We can even show the resonance structure. Protonation of the carbonyl makes the carbonyl more reactive. And we will use that a good bit as an activation step. We can show such a structure, or we can just do it like this. Protonated, we know that's more electrophilic. Water adds, kicks electrons up. The oxygen gets what it wants, goes neutral. From here, we have to take care of proton, but we're on our way. Mechanisms we'll see will be the two-step additional elimination, but there will be steps in between where we have to take care of the proton. Okay, there's other things in here. Including on the very back. On the very back, we have instead of a carbonyl, we have a P double bond O. Take a look at this. The P double bond O, similar chemistry, much less common. Important application. Some Korean half-brother just got axed or something. They didn't poison him with sarin. They poisoned him with VX. VX is very similar to sarin. Okay. All it takes is a wee little bit and very toxic. Chemistry is very similar, additional elimination chemistry. Okay, green sheet. So to review the intro that we just looked at, we'll be using that chemistry here. First though, let's look at a couple of new ways to make carboxylic acids. We looked at the old ways as a review. You should be familiar with those ways, the old ways. New ways, reacting a Grignard reagent with CO2. You take, for example, this guy here, magnesium. We make Grignard reagent, right? Oxidative addition of magnesium. We know this essentially reacts as if it's a carbanion, right? Nothing new there. But CO2. CO2 has Lewis structure like this. Carbon with two carbonyls. This anion, now they're both pooling, and so there's partial positive on this carbon. Okay? And so this adds here. Either way you want to go, then we move electrons onto oxygen. Nucleophilic addition, electrons up to oxygen. Just like on our previous example. Now here we don't have a leaving group. Here, what does this give? Boom, boom. Okay. Now this makes bond to carbon. Electrons up on the oxygen. One carbonyl remains. So we made that bond there. I didn't really need to draw that, did it? There it is right there. Right? How do we get final product? You got to throw in some acid. What's your favorite acid? HCl. Throw in some HCl, you'll protonate the, what do you want to call this anion here? What's the anion of an alcohol called? Alkoxide? This is not with the IDE ending. What do you want to call this anion? It's a carboxylate anion. Carboxylate. It's the anion of a carboxylic acid. Carboxylate anion. Throw in some type of acid, protonate it, there you go. So adding like a Grignard to CO2, if you did this in lab, a lot of times you use dry ice, which is solid CO2. It's a very nice way to make a carboxylic acid. Okay? With this being your nucleophile, right? And then the carboxylate carbon coming from originally your CO2. Pretty nifty, yeah? Okay. A, I was like, where did B go? Okay, A was review. We did that last time, right? Previous methods. These are new methods. Another method is to use cyanide as a synthon. A synthon is like a tool for synthesis. Cyanide. Okay? Good old SN2. Good old SN2, right? We make this bond. Well, that's an acid derivative. Yes? Yeah. And all acid derivatives can be hydrolyzed back to what? Okay, we showed the box. We showed the arrow going all the way back to the top. To what? The acid, using either aqueous acid or aqueous base. Using aqueous acid, I can go to the carboxylic acid. We'll look at this mechanism later when we look at the chemistry of nitriles. Later. It's hydrolysis, just like we showed on that table, all the way to the top. 3 carbons. Where does the extra carbon come from? Cyanide. Total of 4 carbons. So the cyano group was converted to the carboxylate, or the carboxylic acid. It served as a synthon, as a tool that sort of gave the carboxylic acid. Okay, 2 new methods. You got to be careful about which method you use. You can't just use both any time. This compound here. Which of these 2 methods would be better to use to make this compound? I already kind of give you the answer. Why is the cyanide synthon group not good for this? Well, we would back this up to what? Let's see, if we back it up to this, I know I can hydrolyze that to the carboxylic acid. Mechanism later. This backs up to what? Maybe like this, and we're going to react this with what? KCN? Sodium cyanide? Why no good? That's no good. Bromine's on a tertiary carbon. You can't do SN2 on that guy. So this route doesn't work here. Now you can make Grignard here. We've never said you could not make Grignard. You make Grignard and then you throw in your CO2 and then your H plus workup, you can get that. Not quite seeing it? Well, I'm sure when you go home at lunch or this evening, you'll sit down and then you'll see it, right? Yeah, the Grignard method works here, right? So just keep in mind some of your limitations. Okay, there you go. That's we've seen all the ways we're going to make carboxylic acids. 3 or 4 review reactions and then 2 new ways. Okay, so what can you do with a carboxylic acid? That's all right there. Okay, and the first reaction we're going to look at is converting the carboxylic acid to this guy, which is an acid chloride. And as I said, we need to be able to put reagents on all these arrows. So what reagent will do this? So, we can react the carboxylic acid with our old friend thionyl-chloride, and we can get an acid chloride. Now you can also use other things. You can use PCl5. Most likely PCl5 is not going to be in any of your textbooks. But in practice, PCl5 is sometimes used. Thionyl-chloride is a liquid. PCl5 is a solid. I've never used PCl5 for this purpose. Thionyl-chloride is very common. If this was a carbonyl, 2 chlorines, it'd be pretty darn reactive, right? We said with 1. This is a sulfur sort of carbonyl analog. It's called a sulfoxide. Okay, here we go. All we do is react these 2 together. There's no acid catalyst. There's nothing here. We do generate SO2. Which is going to have, what? 1 lone pair, is that right? 1, 2, 3, 4, 5, 6. Looks good. Lone pairs here. Must be 1 lone pair on, yeah, HCl, yeah, boom, boom, boom.
You drew extra one.
So we do generate that. We actually also generated that during test 1 when we reacted an alcohol with thionyl-chloride. So it's going to be the same thing. Okay. These 2 react, that's it. What do you want to do first?
You want to
reactivity
attack
do you have
the
here?
sulfur right there. Yep.
Oxygen is going to attack sulfur.
And then pipe
Okay,
onto
which
the
oxygen
liquid
do you
top.
want to attack?
The
To
low.
use? The top or this one? Why top?
about that? Yeah, that's how you get decomposition.
Which
so you
oxygen
protect the
should
bond.
attack the sulfur?
Bottom.
I'm going to use these back here. I'm just going to call this R group on the side. We have R, oxygen, OH. This is now bonded to sulfur. I'll have to erase some of this. Oxygen up, right? We would never kick off a chlorine. We have a pi bond here, right? Oxygen up. Chlorine, chlorine. Nucleophilic addition. We got a minus. It's got to be a positive because everything's neutral here. You can't just start creating charge, right? Positive here.
Oh, I see.
What next?
So now create the pi bond and take off one of these
You
CLs.
want to concentrate over here. These can come back down. Kick off one of the chlorines. Reform double bond. We still have a plus here, but the minus is now the chlorine that got kicked off. What next? I'm going to get rid of this. We can do resonance. Resonance if we want. Ultimately, what are we trying to accomplish? We want a chlorine bonded to that carbon. Well, we have a chloride. Look at it. It's an upside down carbonyl. Not only is it a carbonyl, it's protonated. So the oxygen's positive. Have we ever talked about protonating carbonyls? Yes, about 20 minutes ago. Look at there. It's a protonated carbonyl. Boom. Give the oxygen what it wants. Okay? Here we go, guys. There's only one mechanism here, but that's overly simplistic. There's nuances. There's nuances. Resonance structure. How would I have known to do a resonance structure? Well, let's see it and then consider nuances. There's a lot of nuance to this chemistry. What does this give? Nope. This is oxygen. Is that there? And everything is neutral? Is that right? Now what do you want to do? Now is where we did our addition. Now we're going to do elimination. Now you might say, well, hold on, isn't the chlorine a better leading group than this oxygen? Oh, that's an argument. We could go backwards. And a lot of times you may. This could be in equilibrium. And maybe it goes back 90% of the time. But occasionally, this is a decent leaving group. It's going to kick this off and we'll go forward. And when it kicks that off, what do we get? Double bond, there's an H here, positive charge. There's your product, it's just protonated. What did we kick off? We kicked off this. This is a decent leaving group because it's resin stabilized. It looks a little bit like a tosylate. except it doesn't have the other oxygen, but it does have a chlorine. Anytime you make a pi bond, kick off a leaving group, what does this give? There's a lone pair here all the way through. Plus what?
Cl minus.
Cl minus. Okay, now what's the final step?
Remove that H.
These electrons take the H. We got to take care of the proton, leave the electrons behind, and there you go.
Why would that attack the carbon?
We're getting into chemistry where if you've been relying on memorization and it's been working, you're less prone to working now. You got to understand the nuances and develop just a feel for the chemistry. Certainly charges, and okay, I'm still seeing lots of incorrect charges or missing charges on mechanisms. Still seeing carbon with pi bonds. Okay. All right. Questions about this? Questions about this?
Why won't it just reattack the carbon when you form a chloride ion?
Tell me where?
Right there.
I want what?
Why won't the chloride ion just attack the carbon again?
This attack which carbon?
That carbon?
Here?
Yeah.
And what's that going to give?
I mean, that's what you did there. The step before.
Attack here?
Yeah.
And to give, you're looking to give what product? A carbon with 2 chlorines?
Yep.
And what, an OH? Maybe a product like that?
Yeah.
Okay, it's not bad. That's not going to be a stable product. Mechanistically, yeah, why not? It's not a stable product. Because anytime you make a pi bond, you kick off a leaving group, it's going to do that. And so the preferred product here is the carbonyl. Carbonyl is a very strong bonding arrangement, and it's driven by the carbonyl. Such a compound is not stable. That compound, you should know, is going to lose HCl. It's going to, because the pi bond, the electrons here, boom, going to kick that off, driven by entropy. Okay, we'll see more of that. We'll see more of that. Okay. Okay, you can convert acids to esters. And the most common is by the Fischer esterification, spelled with a C. Fischer being a person's name, Emil Fischer, I believe, who did a lot of stuff, including like chirality, carbohydrates, Fischer projections, right? Yeah, I think it's the same person. You take a carboxylic acid, treat it with an alcohol and an H+ catalyst, you can get the ester plus water. This is a true equilibrium reaction. We'll discuss that once we do the mechanism. Here we go. You take benzoic acid, ethanol, okay? H+ catalyst, typically strong acids, sulfuric, HCl, HBr. So you can also use, have we ever showed this before? TSCl is tosyl chloride. The P being para. If you look at tosyl, it's got the paramethyl. This is tosyl acid, which would be toluene sulfonic acid. I mean, that's tosyl acid. That's what this is, and it's para relationship. It's a sulfonic acid. Now, if under my hand was another OH, what would that be? Sulfuric acid. So it's got some acidity. But it's an organic acid because it's got the organic, so it's going to be more soluble in things. Also, an advantage of this is this can be dry. This can be a dry acid, pure dry, where sulfuric is always aqueous. And actually, there's a benefit to being dry because we're going to drive equilibrium. We'll talk about that. Okay, so we have an acid catalyst. Anytime you have an acid catalyst, the first thing you want to do in your mechanism is usually protonate something. What do you want to protonate? The carbonyl, right? We looked at that. Protonate the carbonyl. Just call that phenyl. Protonation of the carbonyl to make the carbonyl more reactive, because ethanol is not that strong of a nucleophile. But now ethanol come in here and attack the protonated carbonyl. Okay, we need to draw this out. Oxygen's bonded here. Too many times I'm seeing you guys doing something like this. That's not sufficient enough. You need detail in your mechanism if we're going to understand what's going on. The oxygen is bonded, there's an H there, and there's an ethyl. One lone pair left, positive charge. Nucleophilic addition to carbonyl. We're going to have to take care of this proton. We're about out of time. What do we want to leave here? Not the ethanol, but one of the OHs. How do you make OH a better leaving group? Do we have acid available? Yes, that right there is an acid at this point. Proton transfer. Then we can expel the leaving group. See if you can work it on from there. We're about out of time. Let me see this. We'll pick it up on Friday, right?
Nope.
Huh? What is the, I don't understand what's going on. What's horrible.